So now let's take a look at how you use the derivative, remember that's the slope of the tangent, to determine where a function is increasing, decreasing, or is constant. If I take a look at the graph shown here, if I look at a tangent line to this graph, you will notice that on this left side, no matter where I touch that tangent line, and remember that only touches once, you'll notice that the slope of the tangent is always a positive number. On this side where it's increasing, if I draw tangent lines, again, just barely touch the graph, try to touch it just at one point, you'll notice that the slope of the tangents here are also always a positive number. Okay? So, when the derivative is positive, that means it's greater than 0, the function is rising or increasing. Now, if I look at places where the function is falling, and I look at tangent lines there, you'll notice that for wherever it is falling, the slope of the tangent line is negative. So that's the derivative. So when f prime of x is less than 0, the function decreases. And while we're not concerned with it in this section, I'll show you what happens when f prime of x is equal to 0. Remember, the slope of a horizontal line is 0. So what we're going to learn and talk about in a future section is that when f prime of x is equal to 0, there may be an extreme value. That means a maximum or a minimum. And that is a very useful concept that we will see later on. But right now we're concerned about positive slopes on tangent lines mean the function is increasing, and negative slopes of tangent lines mean the function is decreasing. And the reason we need this conceptually is we don't always have the graph. So we can use this when we have an equation versus a graph. So let's talk about critical numbers. The critical numbers for a function f are those numbers, we call them C, in the domain of the function where the derivative is 0 or where the derivative does not exist. So, for example, when you have a 0 denominator, okay? A critical point is a point with the x-coordinate, that is that c value we found by setting the derivative equal to 0, and a y-coordinate of what you get when you put c, that critical number, back into the function. So the critical numbers are the x values only, okay? These are x values only. And the critical point is where you have an x and a y, and to find the y, you take your critical number and you put it into the original function. Now here's an important note. Although values that make a function undefined are not by definition critical points, because remember it says it has to be in the domain, okay? They're not critical points, but they have to be considered when we're looking at intervals of the function's behavior, such as increasing and decreasing. So a reminder, if the derivative is greater than 0, the function is increasing. If the derivative is less than 0, the function is decreasing. If the derivative is equal to 0, that would be a constant, a horizontal line. So the function is constant. And there could be an extreme value. Just like we saw here, you might have a high value or a low value there. Just depends on the function. So when we're given the equation, that's why we need to use the derivative. I don't have a picture of this, and even if I had the graph, the values could occur at decimal values, which are impossible to read from the graph. So we need to do it algebraically. So my function f of x is 2 plus 3 plus 3.4x minus 0.7x squared. Don't have a graph, so I'm going to take the derivative. The derivative of 2.3 is 0. The derivative of 3.4x is 3.4. The derivative of minus 0.7x squared is 1.4 times x. That's just your power rule. Now, I want to figure out where this derivative is positive or negative, so I set it equal to 0. And I solve that. I'm going to move the 1.4 to the other side by adding it to both sides. So 3.4 equals 1.4x. Divide both sides by 1.4. And 3.4 divided by 1.4 is a decimal. So instead, what I'm going to do is do this as an exact fraction, so I don't have to round. I'm going to move these decimals. It's a fraction. You multiply the top and bottom by 10. So I did that, and I get a 34 over 14. And that's going to reduce to 17 over 7. So that's my critical number, 17 over 7. I will put my critical number on a number line. So 17 over 7 is a positive number. And I need to determine what's happening to the sign of the derivative to the left and the right of 17 over 7. Now, 17 over 7 is approximately 2.4. So I need to pick something to the right. I'll pick a 10. That's clearly to the right. And I'll pick something to the left. That's going to be 0. Now, these are my test points. So I'm going to test 0, and I'm going to test 10. All right, so I can see what's happening from negative infinity to 17 over 7. That's the left-hand side of the critical number. And then from 17 over 7 to positive infinity is what's happening on the right-hand side. And you only have to check one value, because if one of them is positive, they're all positive. If one of them is negative, they're all negative. So inside my derivative, I need to do f prime of 0. So that's 3.4 minus 1.4 times 0. That's 3.4 minus 0 is 3.4. So the derivative is positive on the left-hand side. That means the function is increasing here. Now, I can't just assume it's decreasing on the other side. Sometimes it goes increasing, increasing. So we have to check. Our other test point, f prime of 10, is going to be 3.4 minus 1.4 times 10. That's 3.4 minus 14. Doesn't matter what the actual number is. This is negative. So it's going to be decreasing. So it's decreasing on this side. It's increasing from negative infinity to 17 over 7, and it's decreasing from 17 over 7 to positive infinity. And make sure that you use open intervals, and that is parentheses on both ends.